Hi, Calculus. Okay, we are going to go through these optimization problems because optimization is hard and we're apart. Okay, we have 4,000 meters of fencing that's going to enclose a rectangular plot. So that right there is giving us a perimeter. All right, and the given information is always the constraint. So that is our constraint. So let's keep going through. It borders a straight river. We do not fence the side along the river, and we're looking for the largest, right here, largest rectangular area. So that is what we are trying to maximize. All right, so this right here is our objective. Okay, so we draw the picture. Here's our fun little river. Here is our rectangle along the river. So we need 3 side lengths, all right? So we need an X and we need 2 Ys. So there's our picture and there's our variables. We talked about the constraint. The constraint function is the perimeter. Our perimeter is 4,000, that's given to us. And the perimeter of this particular rectangle is Y plus X plus Y. So that gives us X plus 2Y. Our objective, we're trying to maximize area. We talked about that, and the formula for the equation for the area of a rectangle is just base times height, X times Y. Okay, so we are going to take this constraint right here. You always take the constraint and you solve it for one variable. So I'm going to solve that for X because X is easier than Y. All we have to do to solve for X to get this X by itself is to subtract off 2Y. All right, so I'm going to subtract 2Y from both sides. So that gives me negative 2Y plus 4,000 is equal to X. All right, so that is my solved constraint. And you don't have to put it down twice if you don't want to. But X is equal to negative 2Y plus 4,000. So that's our first step with optimization. You take your constraint and you solve it for one variable, pick the easiest. Now we're going to take that constraint right here and we're going to plug that into our objective equation. So I'm going to go down here to step 5 and I'm going to write my objective equation, X times Y. But I'm going to plug in my constraint. My constraint is equal to X, so I'm going to plug this in right here. So area is equal to, I'm going to put a blank set of parentheses in for X, times Y, and then inside X is equal to negative 2Y plus 4,000. All right, so I just plugged X is equal to this right in here. All right, now my goal of this is to take the derivative. All right, I don't want to leave it like this because that would be a power rule, but if I just distribute, I can simplify. Okay, so we simplify, so to take the derivative. All right, we want an easy derivative. So if we simplify, hello, that's not what I wanted to do. I need to distribute the Y. All right, so I'm going to go up here. A is equal to, if I distribute that Y to the first term, I get negative 2Y squared. And if I distribute the Y to the second term, I get plus 4,000Y. Alrighty? So that is my new objective equation right there. Alrighty? So again, recap. You take your constraint equation and you solve it for the variable, the easiest variable, and then you plug it into your objective and you simplify it to the point that you have an easy derivative. This is going to be all power rules. All right, so we go down to step 6. We take this equation right here and we take the derivative. So A, of course, becomes A prime, and this is all power rules. The derivative of negative 2Y squared is negative 4Y. And then the derivative of 4,000y is just 4,000. So there is my derivative. All right, now I do the first derivative test. So I set the derivative equal to 0. 0 is equal to negative 4y plus 4,000. Now I simply solve for y. So we got some fun, easy algebra. We're going to subtract 4,000 from both sides. So negative 4,000 is equal to negative 4y. Now we can simply divide by negative 4. Those cancel out. So my y is equal to positive 1,000. All right, now I need to prove that that's a maximum. So that is my first derivative test. Okay, so you set up your number line. You put that x-intercept, that critical point, on your number line, and you label your rows. We're going to use the derivative to tell us about the original function. All right, this is the first derivative test. So that's what's in y equals, is this first derivative right here. Put this in your calculator in y equals. Start your table at 1,000. Look to the left of 1,000. What kind of y values does your derivative have? I'm seeing positive y values there, which means over this interval right here, our original function is increasing. If your derivative is positive, your function is increasing. Now, to the right of 1,000, I am seeing negative y values, which means that over this interval, my function is decreasing. All right, and that just proved that 1,000 is a maximum, and that's what we need. All right, so that is my y. Let's remember that's the y. Okay, so our dimensions, we know that y is equal to 1,000. We have to find x. To find x, you always go back to your solved constraint equation. You're going to use the solved constraint. All right, so that's up here. Where's my solved constraint? Right here. We're going to use that. That's already solved for x. All right, so we're going to take x is equal to negative 2 times y plus 4,000. And we're going to plug y in, and we know that y is equal to 1,000. All right, so negative 2 times 1,000 plus 400. That's giving me an x value of 2,000. Nice, easy numbers here. All right, and we should probably have units. So I think if I sneak back up here and look, it is meters. So those should have meters. And then to find the area, we use the objective. All right, our objective equation is x times y. So 1,000 times 2,000 gives us, ta-da, 2 with, it looks like we need 6 zeros. And that would be meters squared. All right, so there's your first optimization problem. We're going to go do number 2 now. Okay, problem number 2. We are going to build a rectangular stock pen using 600 feet of fencing. So there's my given information. If we're fencing around something, that's perimeter. So right here, that is our perimeter. And because it's the given information, that will be our constraint function. All right, then we keep reading. We're going to use part of this fence to build a fence across the middle of the rectangle. So here's the rectangle. I kind of drew the diagram for you. You're welcome. And here's the fence across. All right. We want to find the length and width of the rectangle that gives the maximum area. So whatever you're trying to maximize or minimize, that is your objective function. So that's our objective. We need a maximum area. All right. So our diagram is right here. We need 2 lengths, horizontal lengths, so I'm just going to call those x's. All the way across is x, and then all the way across the bottom is x. All right, and then we have 3 vertical lengths here. We need this length, I'm going to call that y, and this is the same length, another y, and this length. So for the fencing, we need 3 y's and 2 x's. So let's go to the third problem here. Our constraint function we talked about is perimeter. The equation for the perimeter of this particular picture up here, well, our perimeter is equal to 600. That's given to us. And we have 2 x's plus 3 y's. Okay, our objective function we talked about is area, and the formula for the area of a rectangle is x times y. Okay, so we are going to take the constraint equation right here and we're going to solve it for a variable, x or y. In this case, it doesn't matter which one you use because both 2 and 3 go into 600. So you can pick any one you want. I am going to pick y. All right, I'm going to solve this for y. All right, if you want to pick x, go crazy. You'll get the same answer, I promise. All right, to solve for y, we're going to subtract off 2x to start with. So I have negative 2x plus 600 is equal to 3y. And here, make sure you divide all three parts by 3 to get y by itself. And that's the mistake kids make. All three parts have to be divided by 3. Okay, so this cancels here. So I have y is equal to, right here, this gives me negative 2/3 x. So negative 2/3 x. And this right here, 600 divided by 3, gives me plus 200. So there is my solved constraint. And that one you want to keep track of. That's one you're going to come back to at the end always. Okay, so now I'm going to take my objective equation and I'm going to plug this into it for y. So I'm going to write my objective. Area is equal to x times y. I'm going to put a blank set of parentheses. And now instead of y, I'm going to put what y is equal to right here. So I'm going to take this right here, y is equal to, I'm going to plug it in right there. Negative 2/3 x plus 200. Okay, now remember, your goal is to be able to take the derivative of this. So we want to get it to the point where the derivative is easy. If I left it like this would be a product rule, this times this. But if I simplify it by just distributing, then I can get it down to power rules. All right, so I just have to distribute. All right, so a is equal to, if I distribute here, I get negative 2/3 x squared. And if I distribute here, I get plus 200x. All right, so that is my new objective. A is equal to negative 2/3 x squared plus 200x. All right, on to the next step. Now I need to find a max or a min, and that's the first derivative test. So I take this and I take the derivative. So the derivative of a, of course, we just call it a prime. This is all power rules. The derivative of negative 2/3 x squared is, well, I take 2 and multiply it by negative 2/3, multiply tops and bottoms. I get negative 4/3 x. And then the power rule here, the derivative of 200x is just plus 200. So there's my derivative. Now I set my derivative equal to 0 and I solve for x. So the first thing I'm going to do is subtract off 200. So I have negative 200 is equal to negative 4/3 x. Now I need to get rid of this fraction. The easiest way to get rid of a fraction, of course, is to multiply by its reciprocal. So I'm going to multiply, I'm going to sneak it in here, I'm going to multiply that by negative 3/4. And then I have to multiply over here by negative 3/4. All right, and I'm going to make 200 a fraction. Okay, so now I'm going to go over here and I'm going to be ready to roll here. These all cancel out. I've got x is equal to. Now right here, if I multiply across the top, I have 3 times 200. So that, of course, gives me 600. And if I divide 600 by 4, that gives me 150. All right, so my critical point is 150. All right, so now I need to do the first derivative test. So I set up my number line. 150, I put my critical point there. I label my number line. I'm going to use the derivative to tell us about the original function. This is the first derivative test, so I'm putting the derivative in y equals. So right here, this is the derivative. This is what you're putting in y equals, negative 4/3 x plus 200. Now, start your table at 150 and look to the left and to the right. I'm looking to the left and I see positive y values there. So that means my original function is increasing. To the right of 150, I see negative y values. So my original function is decreasing there. So I just proved that this right here is indeed a maximum. All right, and that is my x value. Remember right here, we solved for x here. So x is equal to, so that is one of my dimensions. X is equal to 150. I have to go back now and find y. Now remember, to find y, we use the solved constraint. All right, so that's highlighted above there, and that's the one you always are going to go back to. So the solved constraint is right here, negative 2/3 x plus 200. So y is equal to negative 2/3 x plus 200, and I plug in x there. My x, of course, is 150. All right, so now when I simplify that, if I multiply tops and bottoms here, 2 times 150 is 300. 300 divided by 3 is 100, and that would be negative 100, and then negative 100 plus 200 would give you a y value of 100. All right, so we need units, so let's check our units up there. It is feet this time, so we need 100 feet and 150 feet for our x, so those are our dimensions. And then for the area, we just multiply our dimensions together. 100 times 150 feet would give us an area of, let's see, 15,000 feet squared. Okay, there's problem 2. All right, we'll go to problem 3. Okay, problem 3, there's a little trick to this one. We're building 6 hotel rooms right next to each other. And the key word is each little room. Each of these rooms has 350 feet squared of floor space. So that is area. So this time, this is our constraint, feet squared. Oops, I meant to do a highlighter there. So that is our constraint. I can't spell constraint. Okay, and that is area. Feet squared is area, floor space. All right, so each of those rooms. So our objective function, oh, that's our constraint. Our constraint is area. So, and we know the area is 350. So 350 is equal to, the formula for the area of a rectangle is x times y. So that's our constraint. Now, what are we trying to maximize or minimize? All right, we want to minimize right there, minimize. So we want to minimize total length of the walls all the way around the walls. That is perimeter. All right, so that is our objective right there. That is our objective, and it is perimeter. All right, so length around the wall. So I probably could have just put it right here. Perimeter. Now, we need variables. So because it says each room, we need every single one of those lengths. So that's what's different about this problem. We need all the walls. All right. So again, the key word here, I'm going to highlight it in yellow, each room. Okay. So it looks like there's 12 X's, and then the vertical lengths right here. How many Y's are there? There's 1, 2, 3, 4, 5, 6, 7. So all of the walls, every single wall. All right, so that gives me a perimeter equation of 12x plus 7y. That gives me every single wall. Now we pretty much do the problem the same way. All right, we're going to take the constraint equation right here, and we're going to solve it for a variable. It doesn't matter which one, because either of those are pretty easy. So I'm going to pick y. All right, so we're going to solve that for y. So 350 is equal to x times y. To get y by itself, we simply divide by x. All right, so y is equal to 350 over x. That is my constraint equation, solved constraint equation, 350 over x. So remember, highlight that one. You're going to come back to it. Okay, so now we plug that in to our objective. So I'm going to bring my objective equation down. Perimeter is equal to 12x plus 7y, blank set of parentheses for y, and I'm going to plug this in for y right here, 350 over x. All right, now we've got some work to do, because again, our goal is to take the derivative of this, and this is a big mess, so we're going to clean it up. P is equal to 12x. I'm going to leave that term alone because that's an easy derivative. But I'm going to multiply these two together. So I'm going to make 7 a fraction. I'm going to put it over 1. So if I multiply tops, 7 times 350 is 2450, 2450, and on the bottom I have x. All right, so there is my new objective equation. Now, again, our goal is to be able to take the derivative of this, all right? And I don't want to have to take the derivative of a fraction, so I can take this x to the first right there, and I can bring it up to my numerator, all right? So that can give me perimeter is equal to 12x plus 2,450 x to the negative 1. All right, these are both my new objectives. I'm going to use this one for the derivative, and I'll probably use this one at the very end to get my perimeter. Okay, we are going to take this function right here, and we are going to take the derivative of it. So we're going to go down here, optimize. That's the first derivative test. So the derivative of p, we call p prime. All right, this is a power rule. The derivative of 12x is just 12. Easy peasy. All right, the derivative of the next term, power rule, negative 1 times 2,450 is negative 2,450, and then it's going to be x to the negative 1 minus 1 is negative 2. You got to make sure you're using the derivative power rule. Okay, now we need to set that equal to 0 and solve for x. 0 is equal to 12 minus. Now, I can't solve for x if I have a negative exponent. So I'm going to rewrite this term. I'm going to keep 2450 on top, but I'm going to move x to the negative 2 downstairs, and it's going to become x to the positive 2. So remember, we have to rewrite this because I can't solve for x with a negative exponent. Now, because this is a fraction, I'm going to make this a fraction too and make my life easier. Now, the easiest way that I can tell you to solve for x when you see this set up is move this over to the other side. Hold on, my kid is playing Minecraft and he's yelling. Hold on, pause. Okay, the quiet has returned. All right, so again, we're going to move 12 over to the other side. We're going to subtract it from both sides. All right, so it's going to look like this. I'm just going to sneak up here. Negative 12 over 1, because I subtracted it from both sides, is equal to negative 2450 over x to the positive 2. Now I can cross multiply. All right, whenever you have a fraction, two fractions with an equal in between them, that is cross multiplication. Your fave. Everybody loves to cross multiply. So if I go this way right here, I have negative 12x squared, and it is equal to this way, negative 2450. All right, now I divide by negative 12, and I get x squared is equal to 2450. Of course, divided by 12 is going to be a decimal. So I'm getting 204.17 when I divide that. All right, so 204.17, and now I simply square root both sides. I don't have to worry about the negative because the side length can't be negative, and I get 14.29. Okay, so there is my x-intercept on my derivative. That's where a max or a min will be. So now we do the first derivative test. All right, so we set up our number line. Okay, hold on, pause. Okay, we put our critical point on the number line, 14.29, and we use the bottom row to tell us about the derivative, and the top row is labeled our original function. This is the first derivative test. So you are graphing the derivative. This is the easiest version to put in your calculator right here. So put this in y equals right now. Start your table at 14.29 and look to the left and to the right. To the left, I'm seeing negative y values. All right, so that tells me that my function is decreasing there. This is looking good. To the right of 14.29, I am seeing positive y values. So that means my function is increasing. If a function goes from decreasing to increasing, that is definitely a minimum right there. So we just proved that our x is equal to 14.9 is a minimum. All right, so don't skip that step. You have to prove that. Okay, now we answer the question. My x is equal to 14.29. I need units, so that is feet. To find my other, I use my solved constraint. All right, you always go back to the solved constraint. All right, so I'm going to move this up so you guys can see better. My solved constraint is, of course, right here. So I just bring that down. Y is equal to 350 over what x is. And x is 14.29. So if I take 350 and divide it by 14.29, I am getting 24.5 feet. All right. And now to find the perimeter, I just go back to my objective equation. All right, my objective equation is all set up for me to find the perimeter right up here. All right, so I use it right here. P is equal to 12 times what my x is. My x is 14.29 plus 7 times my y, which is 24.5. And when we compute that, I'm getting a perimeter of 342.98. And that is just plain old feet. All right, Calc, I hope that helped. Optimization is not easy, a lot of steps. But hopefully just keeping it simple to area and perimeter of rectangles is manageable for you. Please let me know. Join me on Google Meet sometime this week. Take care, Calc. Miss you.